Okay, last thing we need to look at in our unit about solutions are called colligative properties. And basically what that means is there are certain properties of solutions that are affected by dissolving stuff in them. So we're going to look at three specific properties: vapor pressure, boiling point, and freezing point. We're not going to worry about osmotic pressure. So what this means is if you compare the boiling point of an aqueous solution to the boiling point of pure water, the boiling point of the solution is going to be higher. Same thing with freezing point. It's going to be lower than the freezing point of pure water. So we're going to be able to calculate based on how much stuff we dissolve in water, how much does that change the boiling point and the freezing point and the vapor pressure. Now we did talk about electrolytes previously when we introduced the unit, and I want to remind you again that electrolytes have to do with ions. Things are electrolytes because they have ions in the solution that can conduct electricity. So ionic compounds, they break apart into ions when they dissolve. Molecular compounds do not break apart into ions, so they don't conduct electricity. They are non-electrolytes. So we're going to be paying attention to whether we're dissolving ionic compounds or molecular compounds, because that will also make a difference in how much the boiling or freezing point changes. Okay, so let's start with vapor pressure. So when you have a liquid, okay, in a closed container, and you can see we have closed containers here. So this is just pure water. There are some water molecules that will evaporate naturally, and then those molecules, like all of these here that have turned into a gas, are going to cause pressure. They're going to bounce off the surface of the liquid and cause pressure. That's called vapor pressure. Now, when we dissolve stuff in water, what we're doing is we are actually creating a mixture and lowering the surface area. So instead of the surface being just water molecules, then the surface is actually here going to be sucrose, which is sugar, and water molecules. So less of the water will evaporate, which leads to lower pressure. Okay. Now, how many particles we get when it dissolves is going to make a difference. So when something like sugar dissolves and you just get one molecule per substance, it doesn't break apart into ions, that's not going to lower the vapor pressure as much as if we dissolve something that broke up into 2 or 3 particles, and we'll look at that as well. Okay, let's talk about boiling point. So boiling point elevation is the difference between a solution's boiling point and a pure solvent's boiling point. So the formula that we're going to use is delta TB. So delta means change in, like delta, any other delta T, but we're specifically looking at the change in the boiling temperature. That's why it's TB. That's going to equal KB, and this is a constant based on the solvent, okay, times molality. And the molality, this is one thing we haven't looked at yet. We haven't done anything with molality. So now this is where we're going to be using those molality calculations. Now there is one thing I want to add to this formula. When you are calculating the molality of a solution, if your solution breaks apart into more than one particle, meaning if the stuff that you're dissolving is ionic, we're going to add another variable, and it's going to be the variable I. And we're going to say that I is the number of particles. Okay, so if we dissolve something that's molecular, that's a non-electrolyte, we're only going to get one particle, so I is 1. But if we dissolve something that is ionic and we get 2 ions or 3 ions or 4 ions, then we're going to have to multiply by the number of particles, because the more particles there are, the more that boiling point changes. Okay, so these are our constants, our KBs, and the KB is dependent upon the solvent. So if we're dissolving stuff in water, which has a boiling point of 100 degrees Celsius, our KB is 0.512 degrees Celsius per molality. If we use a different solvent, here's the boiling point of that solvent, here is the KB. So we're going to pick the KB based on what we're dissolving the stuff in. Most of the time it's water, but you might need that chart to see any other KBs for the solvents. Okay, now freezing point also changes when you dissolve something in a solvent, and freezing point actually goes down, it doesn't go up. So the freezing point of a solution is always lower than that of a pure solvent, because those solute particles interfere with the water molecules or the solvent molecules being attracted to each other and turning into a solid. Okay? So again, we have our formula here, this time delta TF, so this is the change in the freezing point, equals the KF different constant times the molality, and again we're going to add one more variable, I, and again I is the number of particles. So the more particles there are, the more the freezing or boiling point changes. Okay, so we're going to calculate how much that freezing point changes, and the freezing point is going to go down. All right, here's our table of KFs for water. The freezing point is 0 degrees Celsius. Our KF is 1.86 degrees Celsius per molality. And again, there are constants for other solvents as well as water. Okay, so let's turn all of this into a calculation. So it says sodium chloride, which is salt, is often used to prevent icy roads and to freeze ice cream. What are the boiling and freezing points of 0.029 molal aqueous solution of sodium chloride? Okay, so this idea of colligative properties really does have a useful application. If you've ever made ice cream before at home, you know that you put rock salt in with your ice to freeze the ice cream. Well, like we just said, when you put that salt with the water, the freezing point's going to go down. So the ice cream can actually get colder than 0 degrees Celsius and freeze. The same is true when roads ice over. If you put salt on the roads and you lower the freezing point, then it can actually melt the ice at whatever that particular freezing temperature is. So this is a very useful calculation, a very useful idea that you probably never really thought about in terms of solutions and chemistry. So to do this calculation, it's asking about the boiling and freezing point. So we're going to do both the delta TB and the delta TF formula. So we'll start with the delta TB. So delta TB equals the KB, and we're talking about an aqueous solution, so we're going to use water's constant, which is 0.512 degrees Celsius per molality, times the molality that's given, 0.029. And again, we need that I. Okay, so let's think about sodium chloride. Sodium chloride. When that dissolves, what does it break apart into? It breaks apart into a sodium ion and a chloride ion. So how many particles do we get when sodium chloride dissolves? We get 2 particles. So our I is 2. And when we do that calculation, you can see our molalities cancel. We get degrees Celsius for our answer, and that gives us 0.030 degrees Celsius. Okay, so what does that mean? Well, that means that when you make that solution, the boiling point is 0.030 degrees Celsius above the boiling point of water. And what's the boiling point of water? It's 100 degrees Celsius. So the boiling point of the solution is 100.030 degrees Celsius. All right, now we want to do the same thing for freezing point. So we're going to calculate our delta TF. We're still talking about water, so we use water's KF, which is 1.86 degrees Celsius per molality, times our molality, times the number of particles. Our molality is going to cancel, and when we multiply, we get 0.11 degrees Celsius. Okay, so what does that mean? Well, if you remember, the freezing point goes down. So water generally freezes at 0 degrees Celsius. It's going to go down by this much. So our freezing point is negative 0.11 degrees Celsius. So you have to remember the boiling point goes up, the freezing point goes down, and we will be practicing more of these calculations in class.